Let us begin by gently returning to an idea that has already appeared several times in measure theory, even if only implicitly. That idea is accumulation. Measure theory, at its core, is about assigning size, and integration is about accumulating values according to that size. In this section, we focus on integration with respect to a measure. It is helpful to pause and remind ourselves that integration is not fundamentally about techniques or computations. It is about controlled accumulation. It is about taking values, weighting them by size, and adding them up in a careful and stable way. One way to think about integration is as a generalization of summing weighted values. If we have a simple situation where a function takes only a few constant values, then integration is nothing more than adding those values together, each multiplied by the size of the region on which the function takes that value. This is the starting point. These are often called simple functions, though the name is less important than the idea. A simple function divides space into a small number of regions. On each region, the function is constant. To integrate such a function, we take each constant value and accumulate it according to the measure of the region where it appears. This is slow, careful bookkeeping. Nothing mysterious is happening. What is important is that more complicated functions are handled by approximation. We do not integrate complicated functions directly. Instead, we approximate them from below, or sometimes from above, using simpler functions whose integrals we already understand. Then we take limits. It is worth repeating this idea: integration is built from approximation and limits. At every stage, integration respects control. We never allow accumulation to run wild. We only integrate functions whose growth and behavior are sufficiently regulated by the measure. This is why integration in measure theory feels calm and stable. Everything is done through gradual approximation. Let us pause and reflect on this. Integration is not about finding antiderivatives. It is not about clever tricks. It is about accumulating values in a way that respects size and structure. With this understanding in place, we are ready to talk about convergence theorems. These theorems explain how limits interact with integration. They are among the most important results in measure theory, and they are best understood slowly and intuitively. We begin with the notion of convergence almost everywhere. This phrase means that a sequence of functions converges point by point, except possibly on a set that is negligible with respect to the measure. In other words, the functions may misbehave on a very small set, but that set is so small that the measure assigns it no size. It is important to emphasize that almost everywhere convergence is a weak form of convergence. It does not control how fast convergence happens. It does not control behavior on exceptional sets, as long as those sets are negligible. Because of this, almost everywhere convergence alone is not enough to justify exchanging limits and integrals. This is where convergence theorems come in. The first of these is monotone convergence, also known as the Fubini Theorem. This theorem applies when we have a sequence of functions that increases point by point. Each function is everywhere less than or equal to the next one. The sequence builds upward step by step. The intuition here is very simple and very powerful. If we are accumulating more and more mass in a controlled, monotone way, then the integral of the limit is simply the limit of the integrals. Nothing is lost and nothing unexpected appears. It is worth repeating this idea. When functions increase monotonically, integration and limits commute. The accumulation grows steadily, without oscillation or cancellation. This makes the passage to the limit safe. Closely related to this is Fatou's lemma. Fatou's lemma is a low-bound principle. It tells us that the integral of the pointwise limit is no greater than the limit inferior of the integrals. In words, integration does not create mass out of nothing. Fatou's lemma is often used when monotonicity is absent. It provides a safety net. Even when functions behave irregularly, Fatou's lemma guarantees that the limiting accumulation is not underestimated. Then we come to dominated convergence, which is perhaps the most widely used convergence theorem. Dominated convergence requires two things. First, the functions must converge almost everywhere. Second, there must exist a single integrable function that dominates all of them in absolute value. The idea of domination is crucial. It is about control. The dominating function acts like a ceiling, preventing values from becoming too large. Because of this control, limits and integrals can be interchanged safely. It is worth pausing and comparing these theorems. Monotone convergence relies on order and steady growth. Fatou's lemma provides a general lower bound without strong assumptions. Dominated convergence relies on uniform control through domination. Each theorem answers the same question in a different setting. When can we exchange limits and integrals? The answer depends on structure, monotonicity, and control. Let us now move to the idea of completeness and completion of measure spaces. A measure space is called complete if every subset of a negligible set is also measurable and negligible. In simple terms, nothing small is accidentally excluded. Completion is the process of filling in these missing sets. If a set has measure 0, then all of its subsets should also be measurable. Completion ensures this property. The philosophical intuition here is important. Completion ensures that nothing important is left out. If something is negligible, then all of its parts are negligible as well. This aligns with our intuitive understanding of size. Now we turn to series of functions and integrability. A series of functions is simply a sequence of functions added together term by term. The central question is when we are allowed to integrate term by term. Once again, convergence is the key. If the series converges in a controlled way, then integration and summation can be exchanged. Monotone convergence applies when the terms are non-negative and increase steadily. Dominated convergence applies when the partial sums are controlled by an integrable bound. It is important to distinguish between convergence almost everywhere and convergence in integral. Almost everywhere convergence concerns pointwise behavior. Convergence in integral concerns accumulated behavior. The two are related, but they are not the same. Let us repeat this gently. Pointwise behavior does not automatically imply good behavior under integration. Control is always required. Next, we introduce product measure spaces. The product of two measure spaces allows us to measure size in higher dimensions. Intuitively, it allows us to talk about rectangles and volumes. Fubini's theorem is the central result here. It states that, under appropriate conditions, we can integrate with respect to one variable first, and then the other, in either order. The total accumulation is the same. The intuition is straightforward. Accumulating values over a two-dimensional region can be done by slicing the region in one direction or the other. As long as everything is integrable, the order does not matter. Finally, we briefly mention products of many measure spaces. Countable products allow us to model infinite-dimensional systems. Arbitrary products exist at the conceptual level, emphasizing consistency and structure rather than explicit construction. Measure theory ensures that these products behave coherently. Sizes combine in a stable way. Accumulation remains well defined. Let us now slow down and conclude. Measure theory builds a unified framework for understanding size, accumulation, and limits. Integration is controlled accumulation. Convergence theorems explain when limits and accumulation can be exchanged. Completeness ensures nothing negligible is forgotten. Product measures extend these ideas to higher dimensions.